Hello everyone, I am Chih-Shen, a PhD student in Texas A&M University. My supervisors are Dr. Amir Besdin and Dr. Arash Nushadravan. The presentation topic today is enabling reliable AI-based post-disaster damage assessment using aerial imagery. Let's start with the motivation. What is preliminary damage assessment, PDA? After large-scale disaster like hurricanes, earthquake, PDA is one of the key first steps in the process of seeking a federal major disaster declaration. And then let me show you the flow chart for the post-disaster response. After disaster, the government will conduct PDA. Then they will have the information about where the damage is more severe. Next, the joint damage assessment groups will be formed and assess the damage level in the least destroyed areas. FEMA will then review the result and give the suggestion for the disaster presidential declaration. So why timely PDA is important to a successful disaster recovery? There are two main reasons listed here. First of all, PDA result can help estimate and quantify the damage or loss. Estimation of the number of uninsured houses is very helpful to the recovery process because a large number of uninsured damaged buildings may suggest a great need for additional assistance. Also, PDA can help identify any specific regions or local communities with high social vulnerability. For example, low income, disabilities, senior citizens. They may have been affected disproportionately, maybe due to being exposed to high disaster risk or the improper or insufficient disaster planning, education, and mitigation. During the PDA process, the investigator would collect the data based on the assessment form on the right-hand side. The forms are designed to be filled out very quickly and can help the investigators to easily determine the damage state of each building. Also, there are quantified values to help the investigator to determine the damage state. The forms are actually based on FEMA manual, which is shown on the left-hand side. There are 5 damage states defined by FEMA, ranging from 0 to 4. The damage level increases with the damage state. The description provides simple explanation and quantified value to determine the damage state. For example, if we see the second row, which is damage level 1, the roof cover value is between 2% to 15%. However, depending on the size of the affected area, PDA by traditional ground crews can be tedious and resource intensive. For example, after Hurricane Irma in Florida, several PDA teams on the ground took almost 6 days to cover the disaster-affected areas. Therefore, this research aims to improve the quality and the speed of PDA using deep learning and remote sensing technology. Also, we explore how the success of the deep learning application for aerial PDA can be quantified and benchmarked. Past research has used convolutional neural network, CNN, to classify the damaged building in aerial imagery. And the authors have also trained deep learning model for detecting the location of damaged and undamaged roofs in the hurricane footages with good performance. However, these models only generate a binary output which only predict the presence or absence of visual damage and do not differentiate between various damage states, like the FEMA rating system that we described before. So in this research, we create an in-house dataset based on the FEMA table. Because there are not any semantically rich dataset with annotation of disaster damage, and we need such dataset to train and test deep learning models. After the dataset preparation, next I will discuss the methodology of the research, which includes the proposed stack model, what is the law function we use, and the evaluation result of the AI model. Finally, I will present the limitations of the stack PDA and how we address these limitations using multi-view checking techniques. Let's move on to the dataset preparation for AI training. The in-house datasets were created using the web mining methodology from YouTube. Here is one of the videos that we have found and used. This UIV-based video captured top view of destructed residential areas in the Bahamas after the Hurricane Dorian in 2019. We have collected 3 videos from YouTube after Hurricane Dorian. As shown in the figure, we use label box to label the location of buildings and their damage level in the selected frames. In total, we have created about 1,500 samples, which takes about 28 hours by one annotator. Next, I would like to introduce the proposed stack PDA model. Unlike many computer vision tasks that involve detecting everyday objects, for example, dog, cat, car, people, post-disaster scenes are very highly complex, and this would result in a relatively large number of false detections, which will definitely worsen the model performance. So we propose a stack model to address this PDA task. As shown in the figure below, in phase 1, Model L will locate the buildings of input images. Then, in phase 2, Model C can use the cropped images to classify the damage level. Model C is architected based on RetinaNet, and Model C is based on MobileNet. They are both deep learning models. To explain more clearly, the input will be like the top figure on the right-hand side. Next, the Model L can detect the location of buildings, which are covered with boxes. Finally, Model C can classify the damage level of each building. For the damage classification model training, we replace the typical cross-entropy loss with the square of Earth's mover's distance, EMD square, to address the ordinality of damage level classes. To explain this in the figure, consider a sample with the ground truth of damage level 0. Let's also assume 2 predictions A and B. These 2 predictions differ only in the second and third element corresponding to damage level 1 and 2. The cross-entropy loss of both prediction A and B are the same, but we can notice that prediction A is closer to the ground truth. Therefore, prediction A should be better than prediction B, and this conclusion cannot be reached by consider the cross-entropy loss. However, by using EMD square, prediction A is found to have a smaller EMD square than the prediction B. So let's move on to the evaluation result of the trained AI models. Model L was evaluated to achieve 65.6 AP for the building localization. The table presents the confusion matrix of the Model C, the damage classification model. Overall, Model C achieves 61.4 accuracy. At first glance, 61.4 seems not very promising. However, human performance in similar scenarios is around 70%. And also human judgment is subjective, which would also yield inconsistent results. We also explore the correlation between the accuracy and the confidence output by AI model. This correlation is important to disaster recovery because creating new ground truth data for model training and testing is not possible due to the limited time and resources. And without the ground truth data, we can also use this correlation to estimate model performance from the confidence values. So in this figure, the horizontal axis represents the average confidence values in 10% increments, ranging from 20% to 100%. In each interval, the average accuracy of samples belong to that interval is shown on the vertical axis. For example, the group containing the samples with prediction confidence values between 80% to 90% has an average prediction accuracy of 66.7%. The final part is the multi-view tracking implementation. There are some limitations for the stack model. For example, in the sequence of the frames as shown in the figure, UAV may capture different perspectives of the buildings. Also, building damage level are determined based on what is visible, so only one frame may not necessarily represent the entire extent of damage. Building upon our stack architecture, we propose a three-step process for overall building damage estimation by implementing object tracking and statistical inference. Deep sort is used to track multiple Model L detections of the same buildings in a sequence of frames. Next, the Model C, the damage classification model, will use these building detections to produce sequence of damage level predictions along with softmax probabilities. Finally, we can estimate buildings' overall damage state based on these detections using statistical inference like the maximum or average or Bayesian approaches. In summary, this study improved AI-assist model for post-disaster PDA using aerial imagery. And to train AI models, an in-house dataset was created for the model training. And also a stack PDA architecture was developed for aerial PDA. And we replaced the commonly used cross-entropy loss with EMD square to account for the interclass relationships. And we benchmark the AI-based PDA model performance, which is 65.6 building localization precision and 61.4 damage level classification accuracy. Finally, a three-step framework was proposed for overall damage estimation by integrating both object tracking and statistical inference. So I'm near to the end of the presentation. I will be very happy to answer any questions you may have. Thank you.